Picture this. Right now, as you settle into this moment, there's a place in our universe where time itself slows to a crawl, where the very fabric of space stretches like taffy, and where the laws of physics as we know them simply break down. A place so extreme that if you could somehow survive crossing its threshold, you might emerge not just in a different location, but in a different time entirely. These aren't the imaginings of science fiction writers. These are black holes, and they may be the closest thing our universe has to actual doorways into the unknown. Welcome back to this quiet corner of the cosmos, where we explore the deepest mysteries of existence with the patience they deserve. I'm so glad you're here, whether you're listening from a cozy bedroom, a peaceful garden, or perhaps while watching the stars emerge in the evening sky. If you found your way to this channel, you're likely someone who finds wonder in the profound questions that keep curious minds awake at night. Someone who sees beauty in the vast scales of time and space that dwarf our everyday concerns. Tonight, we're embarking on a gentle journey into one of the most mysterious phenomena in our universe. We'll explore how black holes challenge everything we thought we knew about reality, how they've revealed secrets about the nature of information and time itself, and why some of the brightest minds in physics now suspect these cosmic enigmas might be far more than just gravitational prisons. They might be gateways to understanding the deepest structures of existence itself. But first, let me share something that might surprise you. In late 2024, astronomers discovered something that shouldn't exist according to our current understanding of the universe. A supermassive black hole gorging itself on matter at a rate over 40 times what physics said should be possible. This cosmic glutton is consuming the equivalent of an entire star every few days, growing at a pace that defies our models of how the universe should work. It's as if we've stumbled upon a cosmic rule breaker, a phenomenon that whispers of physics we haven't yet discovered. And this is just one of the ways black holes continue to shatter our expectations, revealing that the universe is far stranger, far more interconnected, and far more mysterious than we ever dared imagine. To understand why black holes might be portals to the unknown, we need to begin with something surprisingly peaceful: the death of a star. Not all stellar deaths are violent explosions that light up the night sky. Some are quiet affairs, gentle surrenders to the fundamental forces that govern our cosmos. Imagine a star, perhaps 100 times more massive than our sun, reaching the end of its billions-year journey. For most of its life, it's been engaged in a delicate dance, a cosmic balancing act between the outward pressure of nuclear fusion in its core and the inward pull of its own gravity. But eventually, the nuclear fuel runs out. The fusion fires that have kept the star's immense gravitational field at bay begin to fade. What happens next depends on the star's mass. For smaller stars, the collapse is dramatic, but ultimately stable, creating neutron stars or white dwarfs. But for the most massive stars, something extraordinary occurs. The gravitational collapse becomes so intense, so overwhelming, that nothing can stop it. The star's core compresses beyond the point where atomic structure can resist, beyond the point where even neutrons can maintain their integrity. The collapse continues inexorably until something unprecedented happens. The matter becomes so dense that it warps the fabric of space-time itself into a well so deep that not even light can climb out. A black hole is born not through violence, but through this profound gravitational surrender. This process, which physicists call direct collapse, creates something that challenges our most basic intuitions about reality. Unlike the explosive supernova that scatters stellar material, across space, direct collapse preserves the original structure around the dying star. This is why, in early 2025, astronomers made a remarkable discovery that's reshaping our understanding of these cosmic phenomena. They found the first ever black hole triple system, a configuration that shouldn't exist if black holes only formed through violent explosions. At the center of this system sits a black hole, slowly consuming a companion star that spirals ever closer, completing an orbit every 6.5 days. But here's what makes this discovery so extraordinary. There's a second star orbiting the black hole at a vast distance, taking 70,000 years to complete a single orbit. This distant companion tells us something profound about how this black hole formed. If the central star had died in a violent supernova explosion, the shockwave would have torn away any loosely bound objects. The fact that this far-flung companion remains suggests something much gentler happened, a quiet collapse that barely disturbed the cosmic neighborhood. Take a moment to consider what this means. As you listen to these words, perhaps feeling the quiet rhythm of your own breath, you're contemplating a process that mirrors something deeply fundamental about existence itself. Sometimes, the most profound transformations happen not through violence or drama, but through gentle surrender to forces greater than ourselves. This discovery of the triple system represents more than just an astronomical curiosity. It suggests that there are pathways to creating these extreme objects that we're only beginning to understand. It hints at processes in the early universe that may have seeded the cosmos with black holes through mechanisms far more subtle than we previously imagined. Now we arrive at one of the most mind-bending aspects of black holes, a puzzle that has kept physicists awake at night for decades. It's called the information paradox, and it strikes at the very heart of what we think we know about the nature of reality itself. The paradox emerges from a collision between two of our most successful theories, general relativity and quantum mechanics. According to general relativity, anything that falls into a black hole is lost forever, crushed into a singularity where the normal laws of physics cease to apply. But quantum mechanics insists on something different. Information cannot be destroyed. Every particle, every quantum state, every bit of information that has ever existed must be preserved somewhere in the universe. This creates what physicists call a paradox. If black holes truly destroy information, then quantum mechanics is fundamentally wrong. But if information somehow escapes black holes, then our understanding of general relativity needs revision. For decades, this seemed like an impossible puzzle to solve. Then Stephen Hawking made a discovery that deepened the mystery even further. He showed that black holes aren't perfectly black at all. They emit radiation, now called Hawking radiation, through a quantum mechanical process that occurs at the event horizon. This radiation causes black holes to slowly evaporate over time, like cosmic ice cubes melting in the heat of empty space. But here's the twist that makes this discovery so unsettling. Hawking's original calculations suggested that this radiation was completely random, carrying no information about what had fallen into the black hole. If true, this meant that as a black hole evaporated, all the information it had consumed would be lost forever, violating one of the fundamental principles of quantum mechanics. For years, this paradox seemed intractable. Some physicists argued that information was indeed destroyed in black holes, forcing us to revise quantum mechanics. Others insisted that the information must somehow be preserved, perhaps encoded in subtle correlations in the Hawking radiation that we simply didn't understand yet. But in recent years, a remarkable series of theoretical breakthroughs has begun to resolve this ancient puzzle. Through sophisticated mathematical calculations, physicists have now shown something extraordinary. Information does escape from black holes. Particle by particle, the information needed to reconstruct everything that ever fell in gradually emerges in the Hawking radiation. This resolution comes with a profound implication. It suggests that the interior of a black hole and its exterior are far more intimately connected than we ever imagined. The boundary we call the event horizon isn't a one-way barrier into oblivion, but rather a complex interface where quantum information is processed and preserved. As you contemplate this idea, notice how it mirrors something we might recognize in our own experience. Sometimes, what appears to be a final ending, a point of no return, might actually be a transformation we simply don't yet understand. The information paradox teaches us that, even in the most extreme conditions, the universe seems to find ways to preserve what is essential. The story of black holes took a revolutionary turn on September 14th, 2015. On that date, humanity achieved something that would have seemed like magic to previous generations. We heard the universe itself speaking to us through ripples in the fabric of space-time. 2 laser interferometer detectors, one in Louisiana and one in Washington state, simultaneously detected a subtle stretching and compressing of space itself. The signal lasted less than a second, but it carried information from one of the most violent events imaginable: the merger of 2 black holes, each roughly 30 times the mass of our Sun, colliding at nearly the speed of light in a galaxy over 1 billion light-years away. This detection of gravitational waves opened an entirely new window into the cosmos. For the first time, we could observe the universe not through light, but through the medium of space-time itself. And what we discovered through this new sense was both beautiful and deeply mysterious. The gravitational wave signal told us a story of cosmic violence on an unimaginable scale. In the final moments before merger, the 2 black holes spiraled around each other hundreds of times per second, each orbit releasing more energy in gravitational waves than all the stars in the observable universe emit in light. When they finally touched, they formed a single larger black hole, and in the process converted the mass of approximately 3 suns directly into ripples in spacetime. Think about that for a moment. 3 times the mass of our Sun, the star that powers all life on Earth, was transformed into pure gravitational energy and sent cascading through the universe as waves in space and time itself. These waves travelled for over 1 billion years, gradually weakening but never truly fading, until they finally reached Earth and caused our detectors to move by less than 1/10,000th the width of a proton. Since that first detection, we've observed hundreds of these cosmic collisions. Each one has taught us something new about the nature of black holes and the extreme physics that governs their behaviour. We've detected mergers of black holes with masses we didn't think could exist, systems that challenge our understanding of how these objects form and evolve. One of the most remarkable discoveries came in 2024 when gravitational wave detectors observed the merger of 2 black holes that created a final object with a mass of 225 times our Sun. This was the most massive black hole merger ever detected, involving objects so large that conventional theories of stellar evolution say they shouldn't exist at all. These observations have revealed that the universe is filled with black holes of all sizes, from stellar remnants to supermassive giants, and that they're constantly merging and evolving in ways that reshape the cosmic landscape. More intriguingly, they've shown us that black holes can form through pathways we never anticipated, suggesting that our understanding of these objects is still in its infancy. As you listen to this, take a breath and imagine what this means. Every second, somewhere in the universe, space and time themselves are being stirred by the dance of these invisible giants. The very dimension through which you move and experience reality is alive with waves from cosmic events of unimaginable power. You are, quite literally, swimming in a sea of gravitational ripples from black holes throughout the cosmos. But perhaps the most profound implication of gravitational wave astronomy is what it suggests about the interconnected nature of the universe. These waves carry information across billions of light-years without being absorbed or scattered by intervening matter. They connect us directly to events in the distant cosmos, making us witnesses to the most extreme physics in nature. And this is just the beginning. Future gravitational wave detectors will be sensitive enough to observe black hole mergers throughout the entire visible universe, potentially revealing the formation of the very first black holes in cosmic history. We may soon be able to listen to the gravitational songs of these cosmic giants from the dawn of time itself. Now we come to perhaps the most mind-bending aspect of black holes as potential portals to the unknown, their deep connection to the quantum realm. This connection emerged from theoretical work that seemed almost too strange to be true, but has gradually revealed profound insights about the nature of reality itself. The story begins with a curious theoretical construct called the Einstein-Rosen bridge, proposed in 1935 by Albert Einstein and his colleague Nathan Rosen. These mathematical objects, which we now call wormholes, emerged naturally from Einstein's equations of general relativity. They describe hypothetical tunnels through space-time that could theoretically connect distant regions of the universe. For decades, wormholes remained purely theoretical curiosities, mathematical solutions that seemed to have little connection to physical reality. The problem was stability. Any attempt to traverse such a bridge would cause it to collapse faster than light could travel through it. It seemed that nature had conspired to make these cosmic shortcuts forever inaccessible. But then, in 2017, a remarkable theoretical breakthrough changed everything. Physicists discovered a way to potentially stabilize wormholes using one of the strangest phenomena in quantum mechanics: quantum entanglement. This discovery connected two of the most mysterious aspects of physics in a completely unexpected way. Quantum entanglement is often called spooky action at a distance, a phenomenon where two particles can become so intimately connected that measuring one instantly affects the other, regardless of the distance between them. Einstein himself was deeply uncomfortable with entanglement, but experiments have repeatedly confirmed its reality. The breakthrough came when physicists realized that quantum entanglement might provide exactly the exotic ingredient needed to keep a wormhole open. In this picture, the two mouths of a wormhole would be connected not just geometrically through space, but quantum mechanically through entanglement. The peculiar properties of entangled particles could theoretically provide the negative energy density needed to prevent the wormhole from collapsing. This connection between wormholes and entanglement has led to some of the most speculative yet fascinating ideas in modern physics. Some interpretations suggest that every pair of entangled particles might be connected by a tiny wormhole, making entanglement not just a quantum curiosity, but a fundamental feature of space-time geometry itself. In 2022, physicists took this idea even further when they created what they called the first experimental wormhole, though not in the way you might imagine. Using quantum bits stored in superconducting circuits, they created a holographic representation of a wormhole and successfully sent information through it. While this wasn't a traversable tunnel through space, it demonstrated the deep mathematical connections between quantum information and space-time geometry. These developments have profound implications for our understanding of black holes as potential portals. If black holes are indeed connected to distant regions of space through quantum entanglement, they might function as natural wormholes, with their event horizons serving as one mouth of a cosmic tunnel. The idea remains highly speculative, with no scientific consensus on its validity, but it points toward a universe far more interconnected than our everyday experience suggests. In this view, black holes wouldn't be isolated gravitational prisons, but nodes in a vast network of quantum connections that span the cosmos. As we explore these ideas, notice how they challenge our most basic assumptions about separation and distance. If these speculative theories prove correct, the universe might be more like a vast web of connections than a collection of isolated objects moving through empty space. Every black hole could be a doorway, every quantum entanglement a bridge, every measurement an act of navigation through a cosmos far stranger and more beautiful than we ever imagined. But before we drift too far into speculation, let's return to the solid ground of observation and experiment. Because even as we explore these theoretical possibilities, black holes continue to surprise us with discoveries that expand our understanding of what's actually possible in our universe. And as we'll discover in our next exploration together, the reality of black holes may be even more extraordinary than the most ambitious theories suggest. As we drift deeper into the mystery of black holes, we encounter something that challenges not just our understanding of physics, but our very conception of what it means for something to exist. It's called the event horizon, and it represents perhaps the most profound boundary in the known universe. The event horizon isn't a physical surface you could touch or see. It's more like an invisible threshold, a point of no return that exists purely as a consequence of extreme space-time curvature. Once anything crosses this boundary, it becomes causally disconnected from the rest of the universe. No signal, no particle, no information can ever travel back across this divide. But here's where things become beautifully strange. Recent theoretical work suggests that the event horizon might not be the simple one-way barrier we once imagined. Instead, it might be something far more subtle and interconnected, a boundary that exists in a kind of quantum superposition between being there and not being there. This idea emerges from a fascinating thought experiment proposed by physicists studying the intersection of quantum mechanics and black hole physics. They asked a deceptively simple question: what happens to quantum entanglement when one entangled particle falls into a black hole while its partner remains outside? According to our understanding of quantum mechanics, the entanglement should persist even across the event horizon. The particle inside the black hole should remain connected to its partner outside, maintaining their quantum correlation regardless of the seemingly impenetrable barrier between them. But this creates a puzzle that has profound implications for how we understand the nature of black holes themselves. Some interpretations suggest that this persistent entanglement might create what physicists call an ER equals PR correspondence, where every Einstein-Rosen bridge, every wormhole, corresponds to quantum entanglement between distant regions of space-time. In this view, the interior of a black hole might be connected to its exterior not through any classical pathway, but through the quantum mechanical bonds that transcend ordinary notions of space and separation. As you consider this idea, take a moment to notice how it reflects something we might recognize in contemplative traditions throughout human history. The notion that apparent separation might be illusory, that boundaries we perceive as absolute might be more fluid than they appear. Of course, this remains highly speculative, with no scientific consensus on its validity, but it points toward a universe where connection runs deeper than our everyday experience suggests. This quantum perspective on event horizons has led to some remarkable theoretical developments. In 2022, physicists working with quantum computers created what they called a holographic wormhole, a mathematical representation that demonstrated how quantum information might flow between apparently disconnected regions of space-time. While this wasn't a physical wormhole that could transport matter or energy, it showed that the mathematical structures underlying these concepts are deeply interconnected. The implications extend far beyond black holes themselves. If the event horizon is indeed a more complex quantum mechanical boundary, it suggests that our entire universe might be laced with hidden connections, invisible bridges that link distant regions through quantum entanglement rather than classical geometry. But perhaps the most profound aspect of the event horizon is what it tells us about the nature of information itself. Near the boundary of a black hole, time dilation becomes extreme. To an outside observer, anything falling toward the event horizon appears to slow down, its image becoming redder and fainter until it seems to freeze at the boundary itself, never quite crossing over. This creates what physicists call the frozen star perspective, where from our external viewpoint, nothing ever truly falls into a black hole. Instead, information accumulates at the event horizon, encoded in increasingly subtle patterns of light and energy. In this view, black holes might not be cosmic vacuum cleaners that devour information, but rather cosmic libraries that store it in forms we're only beginning to understand. The gravitational waves we discussed earlier have revealed something extraordinary about the final moments before black hole mergers. These cosmic collisions don't just release energy, They create what can only be described as music, a gravitational symphony played on the strings of space-time itself. In the last few seconds before two black holes merge, they spiral around each other with increasing frequency, their orbital dance accelerating from once per second to hundreds of times per second. Each orbit sends ripples through space-time, creating a characteristic chirp that rises in both frequency and amplitude as the black holes draw closer together. These chirps have been converted into audible sound waves, allowing us to literally hear the songs of merging black holes. Each merger has its own unique signature, a cosmic fingerprint encoded in the patterns of gravitational radiation. Larger black holes produce lower-pitched chirps, while smaller ones sing in higher registers. The final collision creates a brief, powerful crescendo, followed by the steady ring-down of the newly formed black hole, settling into its final configuration. But here's what makes these gravitational symphonies so remarkable. They carry information not just about the black holes themselves, but about the nature of space-time in the most extreme conditions possible. By analysing these signals, physicists can test Einstein's theory of general relativity in regimes where it has never been tested before, probing the fundamental structure of space and time itself. Recent detections have revealed mergers that challenge our understanding of how black holes form and evolve. In late 2024, gravitational wave detectors observed a collision between black holes with masses around 100 and 140 times that of the Sun, creating a final object with a mass of 225 solar masses. This represents the most massive black hole merger ever detected, involving objects so large that conventional stellar evolution models suggest they shouldn't exist. These observations point toward formation mechanisms we haven't fully understood. Some theories propose that such massive black holes could form through the merger of smaller black holes in dense stellar environments, creating a kind of hierarchical growth process where black holes feed on each other across cosmic time. Others suggest more exotic possibilities, including the collapse of primordial gas clouds in the early universe or the formation of an intermediate mass black holes through processes we've yet to discover. As you listen to this, imagine what it means that the universe is filled with this gravitational music. Every second, somewhere in the cosmos, black holes are dancing their final dance, sending ripples through the fabric of reality that carry the songs of their collision across billions of light years. You exist within this cosmic symphony, surrounded by the gravitational echoes of events so powerful they literally shake the foundations of space and time. The future of gravitational wave astronomy promises even more extraordinary discoveries. Next-generation detectors will be sensitive enough to observe black hole mergers throughout the entire visible universe, potentially revealing the gravitational background radiation from countless cosmic collisions throughout history. We may soon be able to map the distribution of black holes across cosmic time, tracing their evolution from the first stars to the present day. But perhaps the most intriguing possibility is that gravitational waves might carry information about physics beyond Einstein's theory. If general relativity is incomplete, if there are additional fields or forces that operate in the extreme environments around black holes, they might leave subtle signatures in the gravitational wave signals. These cosmic laboratories could reveal new physics that we have no other way to access. Now we come to one of the most startling recent developments in black hole physics, a discovery that has profound implications for how we understand the relationship between information, consciousness, and reality itself. It concerns the fate of information that falls into black holes and the remarkable ways that quantum mechanics ensures nothing is ever truly lost. The breakthrough came through a series of sophisticated calculations that revealed something extraordinary about Hawking radiation. While Stephen Hawking's original work suggested that the radiation emitted by black holes was completely random, carrying no information about what had fallen in, more recent analysis shows this isn't quite correct. The radiation is random at first, but as a black hole continues to evaporate, the later radiation becomes increasingly correlated with the earlier emissions. Through these subtle correlations, encoded in patterns too complex for any classical computer to decode, all the information that ever fell into the black hole gradually emerges. Particle by particle, quantum bit by quantum bit, the universe preserves every detail of what was once thought lost forever. This resolution of the information paradox suggests something profound about the nature of information itself. In our everyday experience, information seems fragile, easily lost or destroyed. A book can burn, a hard drive can crash, a memory can fade. But at the deepest level of physical reality, information appears to be indestructible, woven into the quantum fabric of the universe in ways that transcend our ordinary understanding. Some interpretations suggest that this preservation of information might extend far beyond black holes. Recent theoretical work has shown that all massive objects, not just black holes, emit a form of Hawking radiation due to the curvature of space-time around them. This means that stars, planets, and even people are slowly evaporating, releasing information about their quantum structure into the surrounding environment. This is purely speculative and remains unproven, but it points toward a universe where information flows constantly between objects, through quantum channels we can barely perceive. In this view, nothing is ever truly isolated or separate. Every interaction leaves traces. Every quantum measurement creates connections that persist across space and time. As you contemplate this idea, notice how it might relate to your own experience of memory and consciousness. The thoughts you're having right now, the patterns of neural activity in your brain, exist as information encoded in the quantum states of countless particles. That information doesn't simply vanish when a thought ends or a memory fades. It becomes part of the larger information structure of the universe, connected through quantum correlations to everything else that has ever existed. This perspective suggests that consciousness itself might be understood as a particular pattern of information processing that emerges from the underlying quantum substrate of reality. Not that consciousness creates or controls quantum effects, but rather that it represents one of the ways the universe organizes and processes information about itself. The implications are both humbling and extraordinary. If information is indeed preserved at the quantum level, then every moment of conscious experience, every thought and feeling and perception becomes part of the permanent record of cosmic history. Not in some mystical sense, but as a consequence of the fundamental physics that governs the behavior of information in our universe. Recent discoveries have revealed that black holes exist not as isolated objects, but as integral parts of a vast cosmic web that connects the largest structures in the universe. This web, composed primarily of dark matter and dark energy, forms the scaffolding upon which galaxies and galaxy clusters arrange themselves across cosmic space. But black holes play a special role in this cosmic architecture. They serve as gravitational anchors, points where the web's strands converge and concentrate matter and energy. More intriguingly, they may also serve as information processing nodes, places where the quantum correlations that bind distant parts of the universe together are most clearly expressed. This perspective has emerged from studies of how black holes influence their cosmic neighborhoods. When astronomers map the distribution of galaxies across vast distances, they find that the largest structures are organized around supermassive black holes. These cosmic giants don't just sit passively at galactic centers, they actively shape the formation and evolution of the structures around them. The process works through what physicists call feedback mechanisms. As matter falls into a supermassive black hole, it forms an accretion disk that can outshine entire galaxies. The energy released by this process drives powerful jets of particles and radiation that can extend for millions of light years, heating and stirring the surrounding gas and influencing star formation across vast regions of space. But there's something even more remarkable happening at scales we're only beginning to understand. Recent theoretical work suggests that the quantum entanglement we discussed earlier might create connections between black holes across cosmic distances. If true, this would mean that supermassive black holes aren't just gravitational anchors in the cosmic web, but quantum communication nodes that instantaneously share information across the universe. This remains highly speculative, with no scientific consensus on its validity, but it points toward a universe where information and correlation operate on scales far larger than anything we experience in daily life. In this view, the cosmic web wouldn't just be a gravitational structure, but an information network where quantum correlations create connections that transcend ordinary space and time. As you reflect on this possibility, take a breath and consider what it might mean for your own place in the cosmos. If these speculative theories prove correct, then the atoms in your body, formed in the hearts of ancient stars, might still maintain quantum connections to their origins. The carbon in your cells might be entangled with carbon atoms in distant galaxies, creating invisible threads that link you to the furthest reaches of space. This perspective doesn't suggest that your thoughts or emotions directly influence cosmic events, but rather that you exist as part of an interconnected quantum network that spans the entire universe. Every measurement you make, every observation you record, becomes part of the larger information processing system that we call physical reality. The future of astronomy promises to test these ideas in ways we're only beginning to imagine. Next-generation telescopes will be able to map the cosmic web in unprecedented detail, revealing how matter and energy flow through the largest structures in the universe. Gravitational wave detectors will listen for the songs of black hole mergers across cosmic time, tracing the evolution of these quantum nodes from the dawn of the universe to the present day. And perhaps most remarkably, quantum computers may eventually become sensitive enough to detect the subtle correlations that supposedly connect distant parts of the cosmos. If quantum entanglement really does operate on cosmic scales, we might someday be able to use it to probe the structure of the universe in ways that transcend the speed of light limitation that currently constrains all our observations. Take a moment to absorb the implications of these ideas. They suggest that the universe you inhabit is far more interconnected, far more alive with hidden correlations and information flows than anything our ancestors could have imagined. You exist not as an isolated observer looking out at a distant cosmos, but as an integral part of a vast information processing system that spans space and time itself. But as we approach the end of our journey through the mysteries of black holes as portals to the unknown, one question remains. If these cosmic enigmas really do serve as gateways to deeper realities, what does that mean for our understanding of existence itself? And how might these discoveries change the way we see ourselves and our place in the grand cosmic story? These are the questions that will guide our continued exploration of the deepest mysteries of existence, the quiet revelations that emerge when we have the patience to listen to what the universe is trying to tell us about the nature of reality itself. As we reach the deepest layers of our exploration, we encounter something that challenges not just our understanding of black holes, but our most fundamental assumptions about the nature of time itself. What if I told you that the event horizon of a black hole might be less like a barrier and more like a cosmic mirror, reflecting not just light and matter, but the very structure of temporal experience? This idea emerges from some of the most sophisticated theoretical work in modern physics, calculations that reveal the profound ways black holes warp not just space, but the flow of time itself. Near the event horizon, time dilation becomes so extreme that a single second for someone falling in might correspond to millions of years for an outside observer. But recent theoretical developments suggest something even more remarkable might be happening. Some interpretations of quantum gravity propose that the event horizon doesn't just slow time, it might actually create what physicists call temporal entanglement, quantum correlations that connect different moments in time, just as spatial entanglement connects different locations in space. If these speculative ideas prove correct, black holes might serve as natural time machines, not in the science fiction sense of allowing travel to the past, but as cosmic structures where past, present, and future become quantum mechanically interlinked. As you contemplate this possibility, take a breath and notice how it might resonate with your own experience of time. In moments of deep contemplation or meditation, the ordinary flow of temporal experience can seem to dissolve, revealing something more timeless beneath the surface of moment-to-moment awareness. While this remains purely speculative, with no scientific consensus on its validity, it points toward a universe where the rigid separation between past and future might be more flexible than our everyday experience suggests. This temporal perspective on black holes has led to some of the most beautiful theoretical developments in recent physics. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, takes on new meaning when applied to the event horizon. In this view, the two-dimensional surface of the event horizon might contain a complete record of everything that has ever fallen in, encoded in patterns that exist outside the normal flow of time. Imagine what this means for the information we discussed earlier. Every book that falls into a black hole, every thought that was ever encoded in neural patterns, every quantum state that ever existed might be preserved, not just in the Hawking radiation that slowly leaks out, but in the timeless structure of the event horizon itself. It's as if black holes serve as cosmic libraries where all information exists simultaneously, accessible through quantum correlations that transcend temporal sequence. Now we come to perhaps the most profound implication of everything we've explored together: the possibility that black holes might be symptoms of something far more fundamental about the nature of existence itself. What if the universe isn't just a collection of objects moving through space and time, but a vast, interconnected information processing system, and black holes are its most sophisticated components? This perspective emerges from the intersection of several theoretical developments we've discussed. The preservation of information through Hawking radiation suggests that black holes process rather than destroy information. The quantum entanglement that might connect distant regions of spacetime implies a universe where separation is more apparent than real. The gravitational waves that carry the songs of merging black holes reveal a cosmos alive with communication across vast distances. Some interpretations of these ideas suggest that we, physicists call a computational, might be living inside what universe, where physical processes are fundamentally equivalent to information processing operations. In this view, every particle interaction is a calculation, every quantum measurement is a computation, and every observation is an act of data retrieval from the underlying information structure of reality. Black holes, with their extreme information processing capabilities and their ability to encode vast amounts of data on their event horizons, might represent the universe's most powerful computers. They could be the cosmic equivalents of central processing units, handling the most complex calculations required to maintain the consistency of physical law across space and time. This remains highly speculative, with no scientific consensus on its validity, but it offers a radically different way of understanding our place in the cosmos. Instead of being isolated observers looking out at a mechanical universe, we might be integrated components of a vast information processing system, participants in a cosmic computation whose ultimate purpose we can barely begin to imagine. As you reflect on this possibility, notice how it might change your relationship to your own thoughts and experiences. If consciousness really does emerge from information processing patterns in the quantum substrate of reality, then your awareness right now might be more than just a biological phenomenon. It could be one of the ways the universe experiences and understands itself. The discoveries we've explored tonight point toward an extraordinary future for our understanding of black holes and their role as potential portals to the unknown. In the coming decades, technological advances promise to transform these cosmic enigmas from theoretical curiosities into practical gateways for exploring the deepest mysteries of existence. Next-generation gravitational wave detectors will be so sensitive they can observe black hole mergers across the entire visible universe, potentially revealing the formation of the very first black holes in cosmic history. These observations might uncover formation mechanisms we've never imagined, pathways to creating these extreme objects that could reshape our understanding of the early universe. Space-based telescopes will soon be capable of directly imaging the event horizons of black holes beyond our immediate galactic neighborhood, revealing how these structures behave in different cosmic environments. We might discover that event horizons come in varieties we never expected, each encoding information in unique ways that reflect the quantum structure of spacetime itself. Perhaps most remarkably, advances in quantum computing might eventually allow us to simulate the information processing that occurs inside black holes, creating artificial systems that replicate the extreme physics of event horizons in laboratory settings. These quantum simulators could become our first practical tools for exploring the portal-like properties of black holes without the obvious challenges of direct observation. But the most profound discoveries may come from recognizing connections we haven't yet imagined. As our understanding of quantum entanglement, gravitational waves, and information processing continues to evolve, we might discover that black holes are just the most obvious examples of a deeper phenomenon that pervades the entire universe. Take a moment to consider what this could mean for humanity's future. If black holes really do serve as portals to deeper layers of reality, then learning to understand and perhaps even interact with these cosmic structures could open entirely new chapters in our species' development, not through physical travel to other dimensions, but through accessing information and understanding that transcends our current limitations. As we near the end of our journey through the mysteries of black holes as portals to the unknown, it's worth reflecting on how these discoveries are quietly revolutionizing our understanding of existence itself. We began with the image of cosmic vacuum cleaners, objects that devour light and matter without mercy. We end with something far more subtle and profound, cosmic information processors that might hold the keys to understanding the deepest structures of reality. This transformation in understanding mirrors something we might recognize in contemplative traditions throughout human history. What appears destructive or terrifying from one perspective often reveals itself as creative and generative when viewed from a deeper level of understanding. The black hole that seemed to represent ultimate annihilation now appears as a guardian of information, a cosmic librarian that ensures nothing is ever truly lost. The quantum entanglement that connects particles across vast distances, the gravitational waves that carry information through space-time itself, the preservation of information in patterns too complex for any classical system to decode. All of these discoveries point toward a universe that is far more interconnected and alive than our ancestors could have imagined. But perhaps the most remarkable aspect of these discoveries is how they invite us to reconsider our own nature and purpose. If consciousness really does emerge from information processing patterns in the quantum substrate of reality, then every moment of awareness becomes significant not just for the individual experiencing it, but for the cosmic information processing system as a whole. This doesn't mean your thoughts control physical reality or that meditation directly influences quantum events. Such claims lack scientific support and represent misunderstandings of both consciousness and quantum mechanics. Rather, it suggests that consciousness might be one of the ways the universe develops awareness of its own structure and behavior. As you listen to these words, take a breath and notice the profound implications of this perspective. You exist not as an isolated observer, but as an integral component of a vast information processing network that spans the cosmos. Your curiosity about black holes, your capacity for wonder at the mysteries of existence, your ability to contemplate questions that have no easy answers, these might be among the most sophisticated information processing capabilities that the universe has yet developed. The black holes we've explored tonight serve as reminders of just how strange and beautiful our cosmos really is. They challenge every assumption we might have about the nature of reality, revealing depths of complexity and interconnection that boggle the mind. Yet they do so with a kind of elegant simplicity, following the same quantum mechanical and gravitational principles that govern the behavior of atoms and galaxies alike. In the end, the question of whether black holes truly serve as portals to the unknown may be less important than what the search for an answer reveals about the nature of existence itself. These cosmic enigmas invite us to embrace uncertainty, to find comfort in mystery, to recognize that the deepest truths about reality might be far stranger and more wonderful than anything we can currently imagine. And perhaps that's the most profound gift that black holes offer us. Not answers, but better questions. Not certainty, but a deeper appreciation for the magnificent complexity of the universe we call home. Not control over cosmic forces, but a humbling recognition of our place in a reality that exceeds our wildest dreams. As we conclude this gentle exploration of cosmic mysteries, remember that the universe continues to reveal its secrets to those patient enough to listen. Every gravitational wave that ripples through space-time, every quantum correlation that connects distant particles, every photon that escapes from the edge of a black hole carries information about the deepest structures of existence. You are part of that ongoing revelation, a conscious witness to the universe's gradual awakening to its own nature. And in that role, you participate in something far grander than any individual life or death, something as timeless and mysterious as the black holes themselves. Thank you for joining me on this journey through the cosmic portals that challenge everything we thought we knew about reality. Until we meet again in the quiet spaces where wonder lives, keep looking up, keep asking questions, and remember that the greatest mysteries are often hidden in plain sight. If tonight's exploration has stirred your curiosity about the deepest mysteries of existence, I invite you to continue this journey with our previous video on the observer effect, how consciousness shapes reality, where we delve into the profound ways that awareness itself might influence the quantum foundations of the universe. Sweet dreams, fellow cosmic explorers. As we draw closer to the heart of this mystery, we find ourselves contemplating something that exists at the very edge of scientific understanding. The possibility that black holes might be participating in what some theorists call the eternal dance of cosmic information. This idea emerges from recent theoretical developments that suggest the universe might be engaged in a vast ongoing conversation with itself through quantum channels we're only beginning to perceive. Consider for a moment the implications of everything we've explored together. If black holes really do preserve information through the subtle correlations in their Hawking radiation, if quantum entanglement truly connects distant regions of space-time, if gravitational waves carry the songs of cosmic collisions across billions of years, then what we're witnessing might be something far more profound than isolated physical phenomena. We might be glimpsing the universe's method of maintaining coherence across scales that dwarf human comprehension. This perspective has led some physicists to propose what they call the cosmic memory hypothesis, though this remains highly speculative with no scientific consensus on its validity. The idea suggests that every quantum interaction, every particle collision, every gravitational wave leaves traces that become part of a universal information network. Black holes, with their extreme information processing capabilities, might serve as the primary storage and retrieval systems for this cosmic memory. Imagine what this could mean for your own existence. As you breathe quietly, listening to these words, the atoms in your body are participating in countless quantum interactions. Each one might be contributing to this hypothetical cosmic information network, encoding the patterns of your thoughts and experiences into the fundamental structure of reality itself. Not in any mystical sense, but as a potential consequence of the information preservation principles we observe in quantum mechanics. Take a breath here and notice how this idea might shift your relationship to the present moment. If information truly cannot be destroyed, if every instant of conscious experience becomes part of the permanent record of cosmic history, then this very moment of listening and contemplating carries a weight and significance that transcends individual mortality. But perhaps the most profound mystery surrounding black holes as portals to the unknown lies not in their extreme physics, but in what they reveal about the nature of presence itself. Here we encounter a beautiful paradox that has puzzled philosophers and physicists alike. How can objects that seem to represent ultimate absence, regions where nothing can escape, where light itself is trapped, simultaneously serve as cosmic libraries that preserve everything? This paradox becomes even deeper when we consider the recent theoretical work on what physicists call quantum error correction in black holes. These calculations suggest that black holes might not just preserve information, they might actively protect it from corruption, maintaining perfect fidelity across cosmic timescales through mechanisms we're only beginning to understand. The process appears to work through the quantum entanglement networks we discussed earlier. As information falls into a black hole, it becomes entangled with the quantum fields near the event horizon. This entanglement creates multiple copies of the information, distributed across different quantum states, in ways that make it virtually impossible for any of it to be lost or corrupted. It's similar to how advanced computer systems create redundant backups to protect against data loss, except that black holes appear to do this naturally through the fundamental laws of quantum mechanics. The universe, it seems, has built-in mechanisms to ensure that information is not just preserved, but preserved perfectly. In the end, perhaps the greatest portal black holes offer us isn't to another dimension or distant realm, but to a deeper understanding of the mystery that surrounds us every moment. They remind us that the universe operates by rules far stranger than our everyday intuition suggests, where information cannot be destroyed, where quantum correlations transcend space and time, where the boundaries between observer and observed become beautifully blurred. As we've seen tonight, these cosmic enigmas challenge us to embrace uncertainty as a feature rather than a flaw of existence itself. As our gentle journey through the cosmic mysteries of black holes draws to a close, take a moment to breathe and reflect on the extraordinary territory we've explored together. We began with objects that seem to represent ultimate destruction, cosmic vacuum cleaners that devour everything in their path. We end with something far more profound, information processors that might hold the keys to understanding the deepest structures of reality itself. Through gravitational waves, we've learned to hear the universe's own voice, listening to the songs of space-time as black holes dance their final dance across billions of years. Through quantum entanglement, we've glimpsed the possibility that these cosmic enigmas might be connected by invisible threads that transcend ordinary space and time. Through the resolution of the information paradox, we've discovered that nothing is ever truly lost, that the universe preserves every quantum of information in patterns too complex for us to fully comprehend. Perhaps most remarkably, we've seen how black holes invite us to reconsider our own place in this vast cosmic story. If consciousness really does emerge from information processing patterns in the quantum substrate of reality, then your awareness right now participates in something far grander than any individual existence. You are not an isolated observer looking out at a distant cosmos, but an integral part of the universe's ongoing conversation with itself. The question of whether black holes truly serve as portals to the unknown may be less important than what our search for answers reveals about the magnificent complexity and interconnectedness of existence itself. These cosmic mysteries remind us that the deepest truths about reality are often stranger and more beautiful than anything we can currently imagine. Thank you for joining me in this quiet exploration of wonder. Until we meet again in these peaceful spaces where curiosity lives, keep asking the questions that have no easy answers, and remember that you are forever part of the eternal dance of cosmic information that connects all things across space and time.